Every delivery company, airline, and GPS app on Earth is secretly fighting the same puzzle. How do you visit every destination once and get back home efficiently? That's called a Hamiltonian circuit, basically a perfect loop on a graph. You start at one vertex, visit every vertex exactly once, and return to where you began. Sounds simple until you actually try to find one. Unlike an Euler circuit, which only cares about walking every edge once, Hamiltonian circuits are way trickier. In Euler circuits, cost doesn't matter. You're forced to walk every edge no matter what. In Hamiltonian circuits, cost is everything. Two different routes might hit all the same stops, but one could be miles cheaper than the other. Imagine you're a college student based in Chicago, and it's spring break. You and your friends decide to take the ultimate Midwestern road trip. Hit Minneapolis, Cleveland, and St. Louis, then make it back home to Chicago in one big loop. We can model this trip as a weighted graph. Each city is a vertex, and each connection between cities has a weight. In this case, the number of miles between them. Now, gas is expensive and you're a college student, so the goal is clear. Visit all 4 cities exactly once and return to Chicago while traveling the fewest total miles. The most straightforward way to find the best route is to generate every possible Hamiltonian tour that starts and ends in Chicago. Using a tree diagram, we branch out from Chicago to any of the 3 cities, then from there to either of the remaining 2, and finally to the last one before heading back to Chicago. That gives us 6 total paths, but not 6 unique circuits, because some are just mirror images of each other. For example, Chicago to Minneapolis to St. Louis to Cleveland back to Chicago is the same as Chicago to Cleveland to St. Louis to Minneapolis back to Chicago, just in reverse. So really, we only have 3 distinct circuits, which we can visualize like this. Let's add up the lengths of the edges used to find the total cost per graph. The optimal path? Chicago, Minneapolis, St. Louis, Cleveland, Chicago, totaling 1,877 miles. You could also travel this backwards for the same amount of miles. This road trip is a classic traveling salesman problem, or TSP. The goal is simple: find the trip of minimum total cost. Cost could be distance, time, or fuel, and this problem shows up everywhere, from delivery routes and mail distribution to chip manufacturing and even astronomy. Anytime a company needs to visit multiple locations efficiently, they're secretly solving TSP. The strategy we used earlier, listing every possible route and picking the shortest, is called brute force, and while it works, it falls apart fast. Using the fundamental principle of counting, we can get a formula that determines how many unique Hamiltonian circuits exist in a complete graph, where every vertex connects to every other vertex with n vertices. With 6 cities, that's already 60 different routes to check. With 25 cities, that explodes to 300 sextillion possibilities. That's a 3 followed by 23 zeros. Even if you could test 1 million routes per second, it would still take 10 billion years to go through all of them. So brute force is great if you don't mind waiting longer than the sun will exist for most real-life problems. This problem has been studied extensively, so there are many different ways of coming up with a good, but not always optimal solution. I'll talk more about that and how it ties into the Millennium problem, P versus NP, in my next video.